Okay, time to get started. So before we get into the math, a real quick announcement first. And that is that, as I mentioned, oh gosh, I guess it was a week or more ago by now, but I was planning to create a YouTube channel to do the, to give you all the ability to watch video recordings of lectures instead of just putting the files in a folder and making you all find your own MP3 players or your own MP4. I guess MP4. Anyway, I finally did that. So I now have a YouTube channel. There's a link to it on the class website. So if you go to the class website, scroll down. There's a spot that says video recordings or something like that, lecture recordings. Now, instead of pointing to that folder, now that link now points to the playlist for this course. No, excuse me. No, it just points to my YouTube channel. And on the YouTube channel, I actually have a couple of different courses. I have a complete series of lectures from 3 years ago into summer term 2. Same course, same book, same everything. And then also I have a separate playlist for this term. Right? So you should probably, I think your default thing to watch should be this term. Right? But if you want to, get a preview of what's coming up in class, or if you want to get a slightly different point of view on it than what you saw, feel free to look at the other one as well. Okay, so moving along. Going forward, I will only make the videos available in through the YouTube channel. Okay. So you might want to shortcut it or subscribe or whatever they call it, whatever makes that easiest for y'all. Okay, so let me remind you what we've done. We've talked about directional derivatives, and there is a temptation to say that we're done with multivariable derivatives, because after all, look at what this formula says. It says, hey, wherever you might happen to be, whatever direction you might be looking, or whatever speed you might be going in that direction, we have a formula for how to compute how much the function's changing. Right? You give me any input velocity, we have a constructive formula for the corresponding output velocity. That's what derivatives are in the first place, right? Relationship between input and output velocities. So what more is there to accomplish? We have it all, or so it would seem. It turns out there's more to the story, quite a bit more to the story. So I'm going to come at this in stages. I'm going to start with an example of, let's just compute some directional derivatives. Not that we haven't done these before, but anyway, here's a polynomial function. Now it's key for the purposes of this example that this is a polynomial. Okay. And I'm going to compute the directional derivative. Now, but the thing that makes this interesting is I'm not going to specify the velocity vector. I would like to compute the directional derivative as a function of the velocity vector, so that I don't have to go through this calculation every time. If I have a different velocity vector, each new velocity vector I become interested in, I don't want to have to do the whole calculation over again. So we'll just do it in general for a generic velocity vector. Okay, and you go through the process. Don't forget, there's our definition of directional derivative, and blah blah blah, and out comes your answer. Unremarkable at a glance. What you'll notice pretty quickly, though, is that this result is a dot product with the velocity vector. All right, this is 2, 5 dot the velocity vector. Well, that's handy, right? How about that? Said differently, that means that this directional derivative, how this directional derivative depends on the velocity, it's a linear transformation. Neato. Right? We had not noticed this previously. The fact that I have a formula into which I can plug and chug does not reveal that, very often the results of this calculation could instead be computed very conveniently by a linear transformation. Right? So this is a significant eyebrow raiser. Now, of course, all we've done here is show that this is true for that specific polynomial. I claim that this is true, in fact, for all polynomials, and I kind of sketched the argument over the next couple of pages here, and the notation's a little bulky and unwieldy, so let me just kind of point to morally why this is going to happen, and that is, let's look at, when we get to this part of the calculation here, right, we have several terms. We have a constant term, we have a t term, we have a t squared term. There might, if it had been a higher order polynomial, we'd have t cubed terms, etc. Well, look, when you take the derivative, that's going to kill the constant term. Right? Now, subsequently, when you plug in t equals 0, that's going to kill any term that after the derivative still has a factor of t in it. Right? So the only thing that survives this process of taking the derivative and plugging in t equals 0, the only term that survives this process is what ended up being the result. And if you look at that specific term now, this term that survived that process, single value of t, and what that tells you is if you trace back, okay, well, where did these t's come from? The fact that there's a single factor of t means what to me? Well, the factors of t came from the input parameterization, and notice that everywhere there's a factor of t, there is also a single factor of one of the velocity coordinates. Right? So that means that every time we do this process, what's going to remain is going to be terms that have a single factor of a velocity coordinate. In other words, terms that look like this, in other words, it's going to be a linear transformation. So it's not terribly surprising that this always works out for polynomials. So this is worth making a big deal out of. I'm going to state this as a theorem. If you have any polynomial, any polynomial, multivariable polynomial, directional derivatives are computed with a linear transformation. Well, I'm saying, dot product with the vector, but that's a linear transformation. Okay, now this theorem points to a remarkable fact about polynomials. This property that polynomials have is very cool. It's sufficiently cool that it's worth naming this property. The fact that these functions have directional derivatives that can always be computed with a linear transformation, that property is worth naming. So that's what we do here in the next item. We give a definition of a term. Any function whose directional derivatives can always be computed as a linear transformation on the velocity vector, the input velocity vector, I'm going to use the term directional linear. Directional linear. Okay. So yes, what this means then is I'm going to rewrite this theorem that says polynomials have a certain property. I've now named the property directional linear. The theorem then can be restated as all polynomials are directional linear. Okay, so that's just a little bit of lingo. That's very convenient lingo, though. All right, is everybody on board?
What does directional linear like?
What is what?
What is like I don't understand what directional linear means. Like, can you just explain what directional linear means?
You want me to explain what directional linear means? So a function's directional linear if, excuse me, when you're interested in directional derivatives of that function at a particular point, if the way that these directional derivatives depend on the velocity vector, the input velocity vector, is always by way of a linear transformation on that velocity vector. Yeah. Okay. Okay, now you would think, okay, surely this is the entire story, right? We just discovered a remarkable interrelationship between directional derivatives. And it turns out, no, this is also not the entire story. There's more that you can say about these directional derivatives. And let me say this with a deliberate little bit of humor value first. This says, directional linear says that there is a linear transformation that does a good job of approximating how the function is changing. Here's the new upgraded statement I want to talk about. There is a linear transformation that does a good job of approximating how the function is changing. Now, you probably noticed I just said the exact same thing over again, right? So the point of the silly joke is that this new concept that I'm about to describe, so differentiability, it looks at a glance really, really, really similar to directional linear. Stated in a very different way, but I mean, again, let me make the dumb joke again. This says that there's a linear transformation that helps you understand how the function's changing. And so does this. We're just kind of saying it in a different way. Now let me walk you through, well, we're saying something that sounds like that in a little bit of a different way. Now let me walk you through how it is that this statement here actually says that there is a linear transformation that approximates what a function is doing. Let's look at what we've got here. We've got a point A that we're approaching. So we're interested in looking at the values of the function at points X that are near A. Here's how much f actually changed between A and X. I mean, that's the increment, right? F here, f there. What's the difference? That's the actual change in the function. Here, this says, well, let's see what the linear transformation. What is that linear transformation? This hypothetical linear transformation. What does it estimate as being the amount that the function changed? So what we have here in the numerator is we have a difference between the actual change in the function and the linear estimated change in the function. So this numerator is error, right? It's how far off is our estimate of how much the function changed. It would be tempting to say that, well, shouldn't the error be 0? Well, of course it is. Is it enough for the error simply to be 0? And I claim it's actually not. It's actually not that impressive to say that, hey, my error in estimate of the function changing is 0. It's not impressive because it has to be 0. If the function's so much as continuous, f of x has to approach f of a. So this term over here is definitely approaching 0. Over here, well, as x approaches a, this input vector is approaching 0. And all linear transformations are continuous. So the right-hand term is also approaching 0. So this numerator, the error, is approaching 0. It has to approach 0. That's a freebie. That doesn't say anything interesting about t at all. So that's why we divide by the magnitude of x minus a. This says, hey, not only is my error approaching 0, but even if you divide by the increasingly small, the approaching 0 input displacement, even when you divide by that really small thing, that fraction, what we call the relative error, is also approaching 0. And that's a much harder thing to accomplish. So altogether, I mean, let's suppose that this is true. Let's suppose that there is a linear transformation that makes this limit equal to 0. What that means is that this linear transformation is estimating the change in the function so well that even by looking at the relative error, we get 0. Okay, so roughly speaking, so this is, I know it's a lot of talk, right? But this is a seemingly roundabout, but in fact very important way of saying that t is doing a good job of approximating how much this function f is changing. Here, okay, so, yeah. Mm-hmm.
So, did we say that the vector is approaching...
x is approaching a. Yeah.
Just the vector, but then wouldn't x minus a also approach 0?
Yep.
So wouldn't 0 divided by 0?
Nope. So the numerator is approaching 0 and the denominator is approaching 0. but the fraction need not. Right, the fraction, depending on what t is, depending on the this and the that, who knows what that fraction might do. Right? Okay. Yeah. Okay. Right. So, what's the merit of this seemingly much more clunky way of talking about? We have a linear transformation that's approximating how the function's changing. Why is this a good thing? A couple of facts are important. First, every differentiable function is directional linear. So, I mean, we have two different ways of saying what seem like the same thing. And good news, any function that satisfies the one property also satisfies the other property. So, at least they're not in totally, completely different directions. Interestingly, though, not every function goes the other way. Not every directional linear function is necessarily differentiable. Right? So there is a difference between these two terms, even though they both seem to say, come on, there's a linear transformation, it's approximating the function pretty well in some sense. They are actually different as concepts. There are functions that are directional linear that are not differentiable. And let me try to give you a rough idea of why that is. If you look back at the definition of directional linear, note that what we have here, this is a directional derivative. If you look back at the definition of directional derivative, there is a single derivative. You're taking a derivative in a single direction. And said differently, if you think about how derivatives are defined, there is a single variable limit involved in this. Directional derivatives are computed with a single variable limit. In some sense, we're approaching f along a single path. Or we're approaching f along a single straight line, more to the point. Right? And recall, trying to understand multivariable functions by approaching along one straight line at a time, and even if there's a consistency, and hey, every straight line, the function's, doing kind of the same thing, it's nothing to celebrate, right? What about the curved paths? What about the spirals? What about the parabolas? It's such. So what we have here is this is a single variable limit way of trying to understand a multivariable function, and it's ultimately just not a very thorough way of understanding that multivariable function. Differentiability, however, multivariable limit. So here we're using the right tool here. We're using a multivariable limit to understand a multivariable function. This is just a more appropriate, more sophisticated, more complete way of understanding what it means to talk about how a function is changing thoroughly in a multivariable sense. Okay. The other thing is, and this is something I just have to make a vague reference to, and I can't be any more precise at the moment. But if you look down the road at various different theorems that we would like to be able to talk about, and certain properties we would like to be able to talk about for a given function, it turns out that this exact notion of differentiability, not directional linearity, differentiability with the multivariable limit, this is the condition that's necessary to state important theorems later on. You need differentiability to be able to draw certain conclusions. Directional linearity is not sufficient to state those theorems. Okay, so again, that's just foreshadowing. Okay. So a little bit of notation. We're going to use this notation here to represent what that linear transformation is. The linear transformation that realizes the definition of differentiability. Big D for derivative. What function you're trying to understand? F as a subscript. And then comma, the point where you're trying to understand how that function's changing. So D, F, A. And so no surprise that we get the following result here. Let me go ahead and kick in the zoom. We hold this theorem is true Now again, it doesn't look impressive at a glance, isn't it? Didn't I just kind of jumble the letters around? I see a D, an F, an A, and a V on both sides of the equation. Aren't we talking about exact same thing? And very, very importantly, no. What this is saying is that if a function is differentiable, not every directional linear function is. If a function is differentiable, then using differentiability to compute how is the function f changing when you're at the point A moving with velocity v. Using the linear transformation, that will always give you the same answer that you would have gotten by the more naive approach of, I'm looking at the function f, I'm at the point A moving with velocity v, and I'm going to compute with a directional derivative. So the linear transformation, the more sensitive, the more delicate object that may or may not exist, if it exists, it always gives you the exact same values that we already agreed are what we're interested in anyway. All right. This has a couple of nice repercussions, and here's a couple of them. Let me come back down here. Zoom. So, whoops, I can't do that. Okay. These two facts here, and notice what these do is they relate input changes to output changes. That's one of our big points of view on derivatives, multivariable derivatives. They should be a relationship between input changes and output changes. The derivative transformation that we just defined does this. Of course, so did directional derivatives. What we get here, though, is that this thing is now again playing a role of a relationship between input changes and output changes. Directional derivatives are the output change. The derivative transformation is the relationship between input changes and output changes. So the derivative transformation is something that into which you can put in an input velocity, and what comes out is the output velocity. So it's the intermediary as opposed to the result. All right, just like with single variable derivatives, recall in single variable calculus, the derivative is the thing that you multiply by the input velocity to get to the output velocity. Okay, so this recovers that characteristic. Okay, so how do you find derivative transformations? Here's a quick and easy example. We just computed a general formula for that previous polynomial function that we were looking at. Here's a general formula for our directional derivatives. Well, what that means is that this matrix represents the linear transformation. This is the matrix shorthand for the linear transformation that is the derivative transformation here. Or said differently, the derivative transformation is computed with that formula. And I know it is because, well, we know this function is differentiable, and we already computed all the directional derivatives in the previous example, so that must be what the derivative transformation is. Okay. Is that the whole story? Let's summarize. Not only can we compute directional derivatives in every direction, not only are they related by a linear transformation, not only is there this more sophisticated point of view on this idea that involves multivariable limits, but there's a still stricter idea related to differentiability, and that's called continuous differentiability. So, continuous differentiability is a surprisingly familiar idea. It's just like single variable continuous differentiability. A function is continuously differentiable if the partial derivatives exist and are continuous. That's it. It's just like in single variable calculus. What a convenient, refreshing bit of good news. Right? Differentiability is totally different. In Calc 1, a function's differentiable if the derivative exists. Boring. Easy. Convenient. Oh, in multivariable calculus, a function's differentiable if, oh my gosh, well, we've got to talk about relative error and multivariable limits and linear transformations. Oh my, right? It's a big deal to talk about multivariable differentiability compared to the very easy way to talk about single variable differentiability. When you're talking about continuous differentiability, same thing. Derivatives exist that are continuous. End of story. And it turns out this is a stronger condition than differentiability, even stronger. So if a function's continuously differentiable, then it's also differentiable. That's good news. And in fact, this is really, really, really good news. What this says is, if you're interested in proving that a function is differentiable, if your goal is to conclude that some function is differentiable, and you're thinking, oh no, look at that definition of differentiability, there's a multivariable limit, I've got to find a linear transformation, oh my gosh, I'm going to have to compute, I'm going to have to show a multivariable limit exists, I'm going to have to think about all these different paths. Nope. Just check to see if the function's continuously differentiable. That's easy. Compute the partial derivatives. Confirm that they exist and are continuous. No problem. Right? Check that the function's continuously differentiable, and if it is, then the function is also differentiable. Big win. Right? Easy method to apply to conclude an otherwise very difficult conclusion. Okay, so example. There's a function. Is this function differentiable, we ask? Don't bother looking at multivariable limits. Just compute the partials. There's the 4 partial derivatives. 2 output components with respect to 2 input components. They are, as at casual inspection, they are all continuous. And so this function is continuously differentiable and therefore differentiable. No multivariable limit required. Okay, so let me put all these ideas together here. I'm going to skip down to this little diagram, chart, whatever you want to call this, on the next page. This is what I like to call a hierarchy of regularity conditions. So we've talked about several of these already. We just got through talking about this fact, that there is this idea of continuously differentiable, and every function that's continuously differentiable is differentiable. A few minutes ago, we talked about this fact. Both of these statements, both of these terms, differentiability and directional linearity, they're both talking about, does f do a good job of approximating the function? Is there a linear transformation that does a good job of approximating the function? And we saw that differentiability always implies directional linearity. A couple of others, I think it's convenient to have this term directionally differentiable. That just suggests that the directional derivatives all exist. And it turns out that not every directionally differentiable function is necessarily directional linear. There are some functions for which the directional derivatives all exist. No problem, you can compute all the directional derivatives you want, but they don't fit together in a linear transformation. We're going to see an example of one of those. And then partial differentiability means exactly what you would think. The partial derivatives exist. Not every function that's partial differentiable is necessarily directionally differentiable. There are some cases where you can take all the partial derivatives, no problem, but the directional derivatives, some of the directional derivatives might not exist. That's kind of weird. Okay, the interesting thing about this is that this hierarchy is all straight down. So any function that has any one of these properties near the top, you automatically get all the properties down at the bottom. So if you know a function is continuously differentiable, all that comes along for free. If you are interested in showing that all of the directional derivatives of a function exist no matter what the velocity vector is, hey, just show the function's continuously differentiable. Boom, you're done. Very handy. All right. Okay, this is a picture of the graph of a particularly weird function that I think is worth spending a couple minutes on. Here it is. This is a particularly weird and interesting function. Doesn't look that interesting at a glance, Right? So it's a rational function. Polynomial divided by polynomial. It's a big deal. Turns out this is a terribly weird function in a very special way. Now, to more conveniently see that, I make the observation that here's a valid alternative formula for that function. It's r sine 3 theta if you put it in the polar coordinates. By the way, that's a good little exercise. Okay. Just take this formula r sine 3 theta and use angle addition formulas and expand that out and rewrite, and it turns out it's exactly this. You can kind of see from this formulation here, being r sine 3 theta, that how this function changes, well, depending on what direction you are at from the origin, that's going to affect what this sine 3 theta factor is. And there's going to be up, down, up, down, up, down as you go sort of all the way around. And then the r dependence is just linear. Right? Just however far you are away from the origin, well, that's what you multiply by the sine 3 theta. So it's actually pretty easy to see that this is what the function ought to look like. You can see the up, down, up, down, up, down going on there. And you can also see from the origin that no matter which direction you go, straight lines. Right? Okay, by the way, if you want, if you're curious, you can take this formula and pop it into Wolfram Alpha and hit return, and boom, there's a picture, and it's not terribly unlike what I have here. In fact, that's how I drew this. I wish I was that good at art, but I'm not. I put it. Maybe it wasn't Wolfram Alpha. It might have been MATLAB or something. But it was. I put it into some program and let the computer do the work, and then I traced it. Okay. Okay. So let's compute directional derivatives. There's a calculation here. Y'all can go through it if you'd like. But here's the punchline. And again, it's no surprise how this works out. This function, whichever direction you might happen to be going from the origin, starting at the origin. From the origin, theta is constant, so sine 3 theta just sits there. It's constant along that straight line from the origin, and the function's just increasing at a constant rate depending on r. So no surprise that the directional derivatives are easy to compute, and you get this formula right here. And neat observation you can make about this formula, it's simply not a linear transformation. It just isn't. Can you write this as a matrix times x comma y? And it's pretty easily to observe that no, you can't. And to be a little bit more precise about that, if it were a linear transformation, then these two easily computed facts, the fact that this linear transformation applied to 1, 0, this alleged linear transformation, applied to 1, 0, you get 0. Applied to this other unit vector, you get 0. That means that in, in that direction, the value of this transformation is 0. In that direction, it's 0. Then by linearity, it should be 0 in all directions, because every vector is a linear combination of these two vectors. That would suggest this formula should be identically 0, and it's not. So it can't be a linear transformation. And that proves what we wanted to prove. We have therefore successfully found a function where the directional derivatives all exist, but there is no linear transformation that computes them. So it's kind of weird. Okay. So it's a really interesting conversation, I think, about what are all these different regularity conditions? How do multivariable functions all relate to each other? And they're by derivatives. And the answer is it's complicated. Much more complicated than in single variable calculus. In single variable calculus, there's no distinction between these four ideas. In multivariable calculus, there being the derivative existing is enough to say that the function's differentiable. So these are all sort of compressed together. There's no distinction between these in calculus. And Calc 3 here. There it is. How we doing? Everybody on board? One of the last little observation I like to make is let's look at the difference between the strongest condition that we have on the page and the weakest condition we have on the page. These two conditions both say the partial derivatives exist. The only difference between this very strong condition and this, relatively sad and weak condition, or the only difference is the continuity of the partial derivatives. I think that's fascinating, that just the mere fact of the partial derivatives being continuous takes a uselessly weak result and turns it into a more powerful than we usually need result. Just from continuity. That's pretty cool. Okay, let's move on to the next section. Jacobian matrices. This is the natural extension from what we just talked about. We were talking about the derivative transformation. The derivative transformation is super useful. The derivative transformation is a single linear transformation that will compute all of our directional derivatives for us. Wow. How cool. How can I understand this linear transformation better? Well, don't forget, it's a linear transformation. Think back to Chapter 3. Our big lesson from Chapter 3, linear transformations, is that linear transformations can be written as matrices. Right? We can find a matrix representing any linear transformation. So we're going to give that a name. We're going to call it the Jacobian matrix for the function f at the point A. We're going to use that notation to represent it. J, capital J for Jacobi. Mathematicians can't do Jacobi. So the Jacobian matrix for the given function f at the point A. It's just a shorthand representing this linear transformation. By the way, you see now why Chapter 3 is important in this class. Directional derivatives, fine, you can sit there and compute them by hand, brute force, very tediously and inefficiently if you want to. But my gosh, that's inconvenient. Much better to understand that what you're doing is that you're studying a linear transformation. Thus, we need section 3.1. What is a linear transformation? And even better, what we're about to see more of, very convenient to represent that linear transformation as a matrix a la section 3.2. Right? So this one thing then, this Jacobian matrix, is going to be the tool that allows us to very conveniently compute all the directional derivatives that we might want. Okay. So, how do I find the Jacobian matrix? This leads us to, I'm going to say, my favorite calculation in the course. It's just wonderfully convenient. It connects a bunch of ideas that we've talked about so far, and it's short and simple, right? With a super powerful punchline. So here it is. We're going to compute this Jacobian matrix. We're going to compute the Jacobian matrix one column at a time. Turns out to be convenient. How would I compute? I don't know. Let's say the jth column of this Jacobian matrix. Well, here we go. Columns are images of standard basis vectors. Right? That comes from the definition of a matrix. If you want to understand the columns of a matrix, you're looking at the images of the corresponding standard basis vector. Jth column, jth standard basis vector. From section 3.2. From the last section, if you want to understand how the derivative transformation applies to a vector, well, realize that what you're computing is a directional derivative. Right, that's from the last section. And then, from a couple of days ago, what is a directional derivative? How do I compute a directional derivative? Asterisk, my velocity vector is a standard basis vector. Oh, well, your velocity vector is a standard basis vector. Directional derivatives are partial derivatives. So here's the awesome punchline. I mean, this is not a hard proof, by the way. Quick digression. There's 3 steps in this calculation, right? And here's the awesome punchline. Oh, you're interested in directional derivatives, you say? I can compute all of them by just computing some partial derivatives. I can understand the most powerful point of view on derivatives by computationally only doing the world's easiest derivatives to actually crank out. Very handy. Very handy. Such a cool result. Okay, so the columns of the Jacobian matrix are just partial derivatives. That gives us the following formula. There you go. The columns are the partial derivatives. Right, the first column is the partial with respect to x1. Second column is the partial with respect to x2. Notice, of course, f. If f has multiple output variables, then there will be multiple entries in each one of these columns. If f has multiple entries, then the partial of f with respect to x1 has multiple entries, thus multiple rows in the matrix. Okay, writing those out more explicitly. Right, like so. Notice that means that each individual entry in the Jacobian matrix is a partial derivative of one of the output variables with respect to one of the input variables. Partial derivatives, world's easiest derivatives to compute. Now you do have to assemble them in exactly this way, so please make a point of, definitely remember, I'd say memorize, but I think it's better just to understand the underlying idea. Make sure that you remember that columns, right, are telling you partials with respect to a given variable. So said differently, notice that it's all x1s. It's all partials with respect to x1 in the first column. And it's all partials with respect to xn in the last column, in the nth column. Okay, so a common mistake that a lot of students make is that a lot of students remember, oh yeah, the Jacobian, you just compute all the partial derivatives and kind of assemble them into a matrix. And very often students will inadvertently have it the wrong way and have all the x1 partials as a row inadvertently. Right? And of course that doesn't work. Partials with respect to x1, partials with respect to any single input variable are columns, not rows. You've got to make sure to get that straight. Easy to get it messed up. Okay, now don't celebrate too much. There's a temptation to look at this and say, oh, cool. Anytime I can compute all these partial derivatives, hey, world's easiest derivatives. I'm just going to compute partial derivatives and assemble them like so, and I'm just going to use that to start cranking out directional derivatives. It doesn't work. That's not okay. This result, the conclusion that the Jacobian matrix actually does something useful assumes that the function is differentiable. You have to know the function is differentiable. If the function's not differentiable, if you don't know the function's differentiable, and you come back, let's go back to our little hierarchy here. You need differentiability, you need continuous differentiability to show differentiability, and therefore to be able to conclude that directional derivatives are computed with this linear transformation that we now know as the Jacobian, computed with the Jacobian matrix. Simply knowing that the partial derivatives of f exist, this does not, let me use red, danger. Simply knowing that the partial derivatives of f exist, that does not allow you to conclude directional linearity and that you can compute directional derivatives with the Jacobian matrix. It just doesn't work. Don't step on that landmine. It is so easy to accidentally step on. You've got to check differentiability, which of course is most easily done by checking continuous differentiability. Okay. All right. Let's see, where am I? Yeah. Oh, did I? Yeah. There's several examples in here. I'm going to let you look at most of them on your own. I'm just going to return to this one. So this is a rip-off from 4.3.2. You might recall that we computed some directional derivatives. This function, right? And we did this, what I'm going to call the old-fashioned way. We parameterized, for a given input point and given input velocity, we parameterized an input line. We plugged that parametric line into f to get a parametric curve. We took the derivative. We set t equal to 0. We did the whole process. And we got an answer, and it wasn't that bad, I suppose. Look how easy it is now using Jacobian matrices. I can compute directional derivatives using differentiability by way of the Jacobian matrix. The Jacobian is made up of just the partial derivatives of that function. And they're just so easy to write down. Look how easy this is. First column here. Let me do this one at a time. To get the first column, we take the partials with respect to the first input variable. Let's take the partials of this function now with respect to x. And you get y, 0. Boom. Effortless. World's easiest derivatives. Right? Second column comes from taking partials with respect to the second variable, the y partials, x and z. Boom. Effortless. Third column comes from taking partials with respect to the third variable, z partials, and I get 0 and y. So I get this Jacobian matrix. It's falling down simple. Then plug in the point that we were at, right? Which was 1, 2, 0, as I recall. So that's just plugging in, no problem. Our velocity vector that we apply this linear transformation to, our velocity vector in that previous example was 2, 1, 3. And look how your calculation is broken down. In order to get this same answer that you probably remember of 5, 6, all you really had to do was take some super easy partial derivatives and do one matrix multiplication. Matrix vector multiplication. So much easier. Everybody on board? All right, several other examples. I'm going to let y'all flip through. It's morally equivalent. Same kind of thing. Hey, heads up on this this exercise here, JM6. This is a thinker. This has to do with that function we were talking about a couple minutes ago. That function there, that sort of weird. By the way, let me go back to that picture momentarily. Just passed it. Here it is. This picture. Try to make a piece of paper do that. Not going to work. Right? This is a really strange shape, if you think about it. Right? This is not a piece of paper that has it's got a corner in it. I don't even know what to call that. It's not really exactly a corner, because look, if you go from the top of that ridge, as it were, right, down to the bottom of this sort of half pipe that you end up with, right, you could imagine just going, it's a straight line. That's not a corner. It's nice and straight and smooth. You couldn't ask for anything straighter. And that's true along any curve, right? So that's a straight line. Wherever you might start, you can head straight for the origin, keep going past the origin, and you will remain on the surface the whole time. So it's not a corner, and yet something terribly weird is happening there, right? Super weird. There is no single variable analog to this shape. Kind of wacky. Okay. So anyway, that's the this is the curve that's being, or the surface that's being studied in this homework exercise. Where did it go? Yeah, here. And I've made a calculation here of this directional derivative. I've made a calculation using the Jacobian matrix. You see here, And the question is, I want you to decide, is this a valid calculation? Does that make sense? Is this answer plausible? And if not, what is the correct answer? Okay, so anyway, I think it's an interesting question. Again, so the way that you're going to approach this is think about what are the assumptions that should go into this calculation. At a glance, if you take a superficial approach to this question, superficially, there's no hidden arithmetic error in here. I didn't sneak in a -1 times 2 equals 4 to see if you could catch that, right? The arithmetic is not the problem. But this calculation has some underlying assumptions, and you need to decide if those underlying assumptions are correct. So anyway, it'll be a good exercise. Okay, so moving to the next section now, gradient vectors. We're going to consider the following special case. We're going to consider, by the way, all differentiable. Here in section 4.8, every function that we're going to consider here is assumed to be differentiable. Okay, that means we get to use derivative transformations, we get to use Jacobian matrices. That all comes along for free because the functions are all differentiable. The special case we're going to consider here is for functions that are real valued. Functions whose target is R1. So the output values are just real numbers. And y'all probably heard me say this term a lot, just in case you didn't sort of notice the terminology. Real valued function is a way of saying the target is R1. The output is a single real number. Okay, here's what the Jacobian matrix looks like for such a function. Now, that's the exact same formula we wrote down a couple pages back in the previous section. It's just, all the columns are the partial derivatives. It's just that now there's only one output value. That means each partial derivative only has one value. Thus, each column has only one entry. Thus, the matrix only has one row. Everybody on board with how that works out? Any questions about that? Okay, well, so now here's what we do with the derivative transformation, aka the Jacobian matrix. We multiply by velocity vectors to compute directional derivatives. Right, that's why the Jacobian matrix is so convenient. It will compute directional derivatives for us. And that calculation, if you expand that all out, that calculation turns into this. So, again, it's not really all that different from the previous section. Jacobian matrix times velocity vector gives you directional derivative. We already knew that for a differentiable function. Okay. So the observation to make here is that the arithmetic, the mechanics of that calculation are kind of familiar. I mean, it's a dot product, right? It's this times that plus this times that plus this times that, blah, 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 plus this times that. That's how you multiply a matrix times a vector. And if there's only one row in the matrix, then this is overwhelmingly the easiest way to write it. So I'm just going to recopy that and write it as a dot product. And so the directional derivatives that I'm interested in computing, I can compute as a dot product. Now you might say to yourself, okay, this accomplishes nothing. I mean, this calculation here is identical to that calculation there. So who cares? What does this buy us? And what it buys us is the following. We already know cool stuff about dot products geometrically. Right? We have a geometric point of view on dot products. We don't so much have a geometric point of view. I mean, maybe some in a way, right? But matrix vector multiplication, we don't have that same. We don't have the cosine theta. What does cosine theta have to do with matrix multiplication? We don't really have that point of view. Dot products, we have more geometric perspectives. The fact that we have geometric understanding then of the dot product means that we're going to end up with a geometric understanding of this thing that the Jacobian matrix kind of turned into when you stood it on its head, as it were, on its side, however you want to say it. And when you turn that matrix, that row matrix, into a column vector. So having geometric points, if you go on the dot product, is going to give us geometric information on this guy, this thing. And so we're going to give it a name. It's called the gradient. Here's the formula for it. The gradient. This thing that we can use with dot products to compute directional derivatives for real value functions. Call it the gradient. This notation is typical. That is kind of an upside down triangle. You cannot make it like this. That is not okay. If you make it a right side up triangle, this actually means something else. In fact, if you look at the questions on partial derivatives that y'all are going to start, or no, I guess y'all started those partial derivative questions yesterday. There was a exercise where you actually saw this operator, the Laplacian. This is a different thing from the gradient, so make sure to distinguish between those two symbols. And if you have to take a minute to figure out how am I going to make this shape, right? Sit there and practice making it. Go ahead, do what you got to do, but make sure to distinguish it from the other one. Okay. I did that, by the way, when I was y'all's age. I spent, 3-4 minutes sitting there practicing making these triangles until it felt natural. Okay. So yeah, and this is just a restatement of what we already sort of knew, that this thing, by way of dot products, allows us to compute directional derivatives. Okay, so where is that geometric intuition? I got a little ahead of myself. Before I get into the geometric intuition, a quick observation about how this fits in with Jacobian matrices. Look now at a not real valued, look at a vector valued Jacobian matrix like this, right? And we've already talked about how the columns are partial derivatives, right? Every denominator here, every partial that's being taken in this first column, it's all partials with respect to x1. So you might say, and I think this is a nice way to think about it, in the Jacobian matrix, columns correspond to input variables. You could realistically, feasibly call this the x1 column, because all the partials are with respect to x1. Well, for rows, there's something equally sort of comparably convenient, and that is, notice that first row, for example, that is a gradient vector. That is all of the different partials of the same output variable. It's all partials of f1. With respect to the different input variables, partial with respect to x1, partial with respect to x2, etc. Right? So reasonably then, you could call that row, you could say that is the f1 row, because all the partials are of f1, and that row is the gradient of f1. So when you're looking at a Jacobian matrix, columns correspond to input variables, rows correspond to output variables. Okay. That just help you keep it straight. Which way again, there's this constant problem with students inadvertently transposing the matrix. This inadvertently being written as that. It's more common than you would think. So these are a couple of tricks to help you keep it straight. Okay, so geometry. Let's look at this picture here. Here we are in the domain. By the way, just for the sake of clarity, let me indicate. So here's the output values of the function are over here. So the picture that we're going to be looking at is a picture of just the domain. We've got a real valued function f. And suppose that we find ourselves at this point A. So to have something to talk about, let's suppose that we know what the gradient is at that point. Suppose we know the gradient is that vector. And the gradient's a vector. We've got a formula for it. Partials with respect to input variables. It's going to be a vector in the domain. here's a question I would like to propose. Suppose we ask, of all of the different unit vectors representing directions that I could hypothetically move, unit vectors only, mind you, of all these different unit vector directions, in which one of these unit vector directions is the function increasing the fastest? All right, so for example, again, you remember that we did an example several sections back of, we were in a swarm of mosquitoes and we're trying to figure out, okay, how fast is my mosquito concentration decreasing as I move in a particular direction? It was a unit vector direction. Very relevant question is, okay, I'm not married to that direction. Will it decrease faster if I go that way? Just tell me which direction to run, and I will run screaming as fast as I can in that direction. But I want to know which direction makes the concentration change the fastest. All right, what is the direction in which the function is changing the fastest? Pretty reasonable question. Yeah? Got a bunch of different candidates, a bunch of different directions from which I could run. Well, this is a question we can answer with a little bit of algebra, just straight up algebra. So here's how fast the function would be changing. Here, let me do it like this. Those are my directional derivatives using the formula on the previous page. Directional derivatives, unit directional derivative, mind you. Gradient dot direction vectors. My question was, how do I make this as big as possible? I make this directional derivative as big as possible. That means I want to make this formula as big as possible. That means I want this dot product to be as big as possible. And recall that we know, as I foreshadowed, cool geometric information about dot products. This dot product is the product of the magnitudes times the cosine of the angle in between it. The fact that we have this geometric information about the dot product is what's going to help us answer this question we're in today. So I want to make this directional derivative as big as possible. That means I want to make this dot product as big as possible. That means I want to make this expression here as big as possible. By the way, notice that since we're only considering unit vectors, the magnitude of u is 1. So I can throw that away. That means I just want to know, how can I make this expression as big as possible? Let's come back up to our picture here. I'm interested in the product of the magnitude of the gradient let me interrupt myself. Magnitude of the gradient. Keep in mind, I'm considering all possible unit vectors. Which direction can I go? Of all these different unit vectors representing directions, how does the magnitude of the gradient have anything to do with what direction you're going? The gradient vector only depends on where you are. Right? Until you start actually moving, you're still at that point. The gradient vector is independent of which direction you're thinking about possibly running. Right? So the magnitude of the gradient is constant for the purposes of this question as you make your decision. So let me just replace that with c, because this is a great big constant. Oh, that's hard to read. Let me just say c. So what I really want to do then is I want to figure out, how can I make cosine theta as big as possible? Coming up here to our picture, again, we're thinking about all these different unit vectors. How they dot with the gradient. That angle theta there. I want to know, how can I make the cosine of this angle as big as possible? And now I appeal to your memories of trig. Cosine theta is as big as possible when theta is 0. Right? Cosine theta becomes 1 when theta is equal to 0. Let's look at this picture. What happens when theta is 0? When theta is 0, I was going to try to scratch that out. When theta is equal to 0, the unit vector is that way. Right, so I can make my directional derivative as big as possible by choosing the unit vector that points in the same direction as the gradient vector. So that's the answer to our question here. The unit vector is the unit vector pointing in the same direction as gradient f, and of course y'all remember the formula for how to find a unit vector pointing in the direction of a given vector divided by the magnitude. So gradient f divided by the magnitude of the gradient of f. Said differently, the gradient of f is the answer to this question. We now have, I'm going to call some interesting geometric interpretation of gradient of f. This vector, gradient of f, if you find yourself at this point, if you are interested in the values of that function, and if you would like to know which way should I run to make the function f change as fast as possible, go in the direction of the gradient vector points. Right. By the way, the terminology here, I like to call this the direction of fastest increase. The gradient will always point in the direction in which the function f is increasing the fastest. The direction of fastest increase. Where did I write? It's here. See, here it is. Direction of fastest increase. Everybody on board with that calculation? Any questions? Okay. This term, direction of fastest increase, is not as common as I would like. There is a different term that is often used. You'll notice that in the example that I gave here, I did not draw the graph, as y'all know. As you've probably heard more than you would like. I'm not a big fan. Well, I'm a fan, right? But I'm concerned that students over-rely on the idea of a graph. So very importantly, here we're not looking at the graph. We're thinking about mosquito concentration. The pictures we're thinking about in this case are all happening in the domain exclusively. Okay. But now let's imagine if we were looking at a graph. Here's what that would look like. Right here, I've got, here's my domain, and I'm viewing the vertical axis as being my sort of how my target shows up on this picture, and the surface represents, height represents the output value of the function. Well, if you think about it, if you're asking of all the different unit vectors, from this point A, of all the different unit vectors representing directions in the domain, so kind of in the xy plane, of all these different directions in the domain that I could start running, the one that makes the function increase the fastest would be the one that's making the height increase the fastest. And that would mean it's the one that's making the steepest what we call ascent, the steepest ascent. We're climbing the hill that is the graph of this function. We're climbing that hill as steeply as possible. So this direction here, the direction of the gradient, is sometimes called the direction of steepest ascent. That's the more common terminology. Now, again, let me criticize that. It's only representing a direction of steepness if you're looking at a graph, which very often we not only aren't, but can't. Right? So, it's a bad sort of starting point of intuition, in my opinion. I'd rather not think of the gradient as pointing in the direction of steepest ascent. This point of view is peculiar, arguably. Right? So, I push the term direction of fastest increase. And, direction of steepest ascent is what you're going to hear out in the real world more so. Okay. Right. Okay, so next question, related question. Okay, great. So suppose you're going in this direction of fastest increase. We just agreed what direction that is. Great. The mosquito concentration is decreasing as fast as possible. This is great news. I would like some more specifics, please. How fast is the mosquito concentration changing? Very interested in the rate of change of mosquito concentration. What more can you tell me? And the nice handy formula for that, the magnitude of the gradient vector. It's a straight up calculation. Directional derivatives are computed with that formula. That formula simplifies very nicely when we've already agreed that we're going to go in the direction of fastest increase. So U is the gradient vector divided by the magnitude of the gradient vector. Notice that this dot product gives you magnitude squared. Magnitude squared divided by magnitude is magnitude. So straight up calculation, no big deal. Magnitude of the gradient. Okay, so the really nice thing about this is this gives what I like to call a geometric characterization of the gradient vector. The formula we have previously for the gradient vector is algebraic. We have here's the formula. You take the following partial derivatives. It's algebra, and very useful, by the way. Of course, right? You've got to be able to compute things. So algebraic formula. Got to have it. But knowing how to think of it geometrically is also really valuable. So what we have here, these two previous questions we've considered, when you combine the results together, what you have is a characterization of natural interpretations of direction and magnitude. The geometric aspects of that vector, direction and magnitude, are both the answers to very reasonable and interesting questions. The direction is the direction of fastest increase. The magnitude is whatever the unit directional derivative is in that direction. All right, let me say that a little bit differently. The direction is uphill. The length, how steep is it uphill if you're looking at a graph? That makes sense? And ultimately, this all comes from dot products. The fact that we took a matrix vector product with which we did not have particularly good geometric tools, rewrote it as a dot product with which we do have geometric tools. That's why, even though this was a little harder to understand, the gradient vector became easy to understand because we have a connection to dot products. Okay. All right. Couple more minutes. I'm going to do one last thing. And that is talk about the relationship to level sets. Turns out the gradient vector is always orthogonal to the level set of the point that it's on. The level set on which that point is. Yeah. This is a very surprising fact. So let me come back up to this picture here. So, I guess I kind of need the thing here. But so we've got this multivariable function, f, right? Real valued, right? We could talk about, for this real valued function, we could talk about the level sets. Well, knowing that the gradient vector points that way, the level sets, the level set has to be, I wanted a different color. The level set has to be perpendicular to that. And a quick observation about context, notice that the gradient vector always lives in the domain. You can see that from the formula. Level sets, of course, we already know level sets always live in the domain. So level sets and gradient vectors are geometric objects in the same world. They're both in the domain, and there's this wonderful connection between them. They're always perpendicular to each other. And it's actually pretty straightforward to see why. Here we go. So keep in mind, let me go to this picture here. Suppose you're looking at a real valued function here, looking in the domain. So here's the domain of that real valued function. And suppose we're interested in what's happening at that point. that point being on a certain level set. Okay, so at that point, f of a is a certain value. The level set corresponding to that value is a surface that goes through that point. I could compute the gradient vector at that point. Well, the assertion is that this vector is perpendicular to that surface. The way we're going to get our hands on that is think about at that point, that being the gradient vector. Let's think about the process of walking or moving along that surface. But imagine you're, a little ant or whatever, you're walking along this surface, and maybe you walk to that point, at which time you have a certain velocity, right? Well, as long as you're walking along the surface, the value of the function is not changing. F of your position is c. It is constant. It's not changing. You're on a level set. And if something is not changing, I'm just thinking through. If something is not changing, if something is constant, is not changing, that means the derivative is equal to 0. So that means that as you're moving, with that velocity at that particular point, the directional derivative is 0. Wait a second, we just agreed that directional derivatives can be computed with dot products. That's dot product with the gradient vector. If a directional derivative is 0, that means that this dot product is 0. And we all have a knee-jerk reaction. Whenever you see dot product is equal to 0, we know that means perpendicular. So gradients are always perpendicular to the level sets. Okay, a couple of examples. These are pretty straightforward. I'm going to let you all read these examples on your own. I'm going to declare us done with section 4.8. And I owe y'all an email noting the homework assignment. And okay, see y'all later. Have a good day. Some of y'all came in after class had started. For those of you who came in late. I do have to get attendance as well. But so a quick announcement: the video recordings that I have been putting into a folder that was linked on the class website. I'm now done with those folders. I am now going to put all of my video recordings onto my newly created YouTube channel. That YouTube channel is linked from the class website in the same place. So just click on that link. It'll take you to my YouTube channel. You can bookmark it or whatever. And that's how you get the recordings. Okay. See you later.